Good morning, students. In class 2 of the chapter Coordination Compound, I already completed the Orino's theory, the valency bond theory, application of a valency bond theory to different type of complex. Generally, we observe two type of complex having coordination number 6 and a complex having coordination number 4. If a complex having coordination number 6, then expected geometry is octahedral. If a complex having coordination number 4, then expected geometry is either square planar or tetrahedral. In previous class, that is class 2 of the chapter Coordination Compound, already covered the coordination, that means complex having C dot n 6. Again, in that case, under the heading of C dot n 6, that is octahedral complex, it is of two types. One is known as inner orbital complex, one is known as outer orbital complex. That means, if inner n-1 d orbital participate in the hybridization, then it is known as inner orbital complex, low spin complex, or spin paired up complex. On the other hand, if outer d, that is nd orbital participate in the hybridization, then that is known as outer orbital complex or high spin complex or spin free complex. In the previous class, I already completed the inner orbital complex by giving a suitable example. Let us recap that one by giving another one example. Mark that. One example, second example, that is FeCN6 3 minus complex ion. It is the second example, FeCN6 3 minus complex ion. So from this it is clear that here the central metal atom is iron having atomic number 26. Noble gas electronic configuration argon 18. 4s2 3d6. The box-like diagram, it is on the basis of cell 3d 4s 4p. It is 3d 4s 4p 4s2 3d6. Mark that. And from this it is clear that the oxidation state, it is not known, let is x plus 6 into minus 1 is equal to minus 3. On solving, x is equal to plus 3. So B2, that is iron is in plus 3 oxidation state. So its electronic configuration is argon 18 3d5. So the expected box-like diagram is 1, 2, 3, 4. 1, 2, 3, 4, 5. 4s, 4p. It is 3d, 4s, 4p. Mark that. From the formula it is clear that cyanide ion is a strong field ligand. So in the presence of strong field ligand, the unpaired electron get paired up. So third one is FeCN6 3 minus ion. So what happened? Unpaired electron get paired up. 1, 2, 3, 4, 5. 4s, 4p. So mark that. As there are 6 ligands are there, Cn minus, Cn minus, Cn minus, Cn minus. Each ligand donate a pair of electron. So from this diagram it is clear that 2 3d orbital, 1 4s orbital and 3 4p orbital get hybridized, resulting in the formation of D2sp3 hybridization. So from this also it is clear that as there is a presence of one unpaired electron, this complex is paramagnetic nature. Since coordination number 6, the complex is octahedral. Since inner d, that is n-1 d orbital participate in the complex, it is known as inner orbital complex. Inner orbital complex, octahedral geometry, and magnetic character is paramagnetic in nature. It is little idea about inner orbital complex. Next, switch over to outer orbital complex. Next, we discuss about outer orbital complex. Here C dot n is equal to 6. Mark that. In case of coordination number 6, octahedral geometry, when the approaching ligand is weak field ligand, then the inner n-1 d or electron orbital, there is some unpaired electron, they never paired up, never against the Horn's rule, as a result of which the outer n-d orbital, that is 4d orbital, participate in the hybridization, resulting in the formation of outer orbital complex. Since maximum number of unpaired electrons are there, it is also known as high spin complex or spin free complex. Due to the presence of unpaired electron, maximum chances are they are formed paramagnetic in nature. So let us discuss one example. It is between COF6 3- complex ion. So from this example, it is clear that the central metal atom is cobalt, having atomic number 27, noble gas electronic configuration 18, argon 18, 4s2, 3d7. The expected box-like diagram 3d, 4s, 4p. It is 3d, it is 4s, it is 4p. 4s2, 3d7, 1, 2, 3, 4, 5, 6, 7. Then we have to calculate the oxidation number. Let it is x plus 6 into minus 1 is equal to minus 3. On solving x is equal to plus 3. That means cobalt is in plus 3 oxidation state. So its electronic configuration is argon 18, 3d6. 3 electron lost, outermost 2 electron and 1 electron from 3d. So the expected box-like diagram 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. It is 4s. It is 4p. 4s, 4p, 3d. Mark that. As is the weak field ligand, so there is no deviation against the Horn's rule. The electron in the 3d orbital never paired off, as a result of which the outer d orbital, that is nd orbital, or that means 4d orbital, participate in the hybridization. And also it is verified from the experimental facts that this complex is paramagnetic nature. So mark that. Third one, COF6 3- ion. Box like diagram. It is 3d, it is 4s, it is 4p, it is 4d. No pairing of electron. 6 ligand is there. Each ligand donate a pair of electron, forming a complex. So from this it is clear that 1 for s orbital, 3 for p orbital and 2 for d orbital, resulting in the formation of the hybridization, resulting in the formation of sp3d2 hybridization. sp3d2 hybridization. So from this discussion it is clear that it is an octahedral complex as C dot n 6. It is an outer orbital complex because outer d orbital, that is nd orbital, that is 4d orbital participate in the hybridization, and the expected hybridization, that is sp3d2 hybridization, octahedral complex. And since there is the presence of unpaired electron, this complex is paramagnetic in nature. Next, we go to another one example. Second example, NiH2O whole 6 to plus ion. So from this complex it is clear that the central metal atom is nickel atom, atomic number 28. So noble gas configuration, that is argon 18, 4s2, 3d8. The expected box-like diagram. It is 3d, 4s, 4p, 4s2, 3d8, 1, 2, 3, 4, 5, 6, 7, 8. So from this it is clear that we have to calculate the oxidation number. It is not known, let is x, plus 6 into neutral ligand is equal to 6 into 0 is equal to plus 2. On solving, x is equal to plus 2. That means nickel is in plus 2 oxidation state. It loses 2 valence electron. The expected electronic configuration argon 18, 3d8, and the box-like diagram is like this. It is 3d, 4s, 4p, 8 electron, 1, 2, 3, 4, 5, 6, 7, 8. 2 unpaired electron is there. And as it is the weak field ligand, there is during electronic configuration it will obey the Horn's rule, no pairing of n-1 d electron. That means here outer orbital, that is 4d orbital, participate in the hybridization. So mark that, bit 3. NiH2O6 2 plus. Box-like diagram, 3d, 4s, 4p, 4d. It is 3d, 4s, 4p, 4d. 1, 2, 3, 4, 5, 6, 7, 8. Then 6 ligand is there. Each ligand donate a pair of electron. So from this it is clear that 1 s orbital, 4s orbital, 3 4p orbital and 2 4d orbital participate, resulting in the formation of sp3d2 hybridization. Since the outer orbital, that is 4d orbital, participate in the hybridization, so it is known as outer orbital complex. Since maximum unpaired electron is there, spinning is there, so it is known as a high spin complex or spin free complex. And due to the presence of unpaired electron, the complex is paramagnetic nature. It is all about the octahedral complex having coordination number 6. Then switch over to tetrahedral complex or square planar complex having coordination number 4, 1 by 1. Next we discuss tetrahedral complex. Tetrahedral complex having coordination number is equal to 4. Let us discuss tetrahedral complex having C dot and 4. Let us discuss one example, that is NiCO4 tetracarbonyl nickel 0. So from this it is clear that the central metal atom is nickel having electronic configuration 28, atomic number 28, noble gas configuration argon 18, 4s2, 3d8. The expected box-like diagram. It is 3D, it is 4s, it is 4p, 1, 2, 3, 4, 5, 6, 7, 8, 4s. It is the electronic configuration according to Horn's rule and above principle. Point 2, mark that. From this, we have to calculate the oxidation number. It is of central metal atom not known, let it is X, plus 4 into carbonyl neutral oxidation 0, as it is a neutral molecule. Sum of the oxidation number is 0, implies that X is equal to 0. That means nickel is in 0 oxidation state. There is no loss of electron. So mark that. As is the strong field ligand. As the strong field ligand, so electron present in the inner d orbital, that is n-1 d orbital, that is 3d orbital, get paired up. Simultaneously, the experimental study reveals that the complex is diamagnetic. In order to verify the experimental fact, it is supposed that due to the presence of strong field ligand, all the unpaired electron in 3D get paired up, giving one vacant, and that pair of electron in 4s jump to the 3D. Mark that. The box-like diagram. It is 3D, it is 4s, it is 4p. All electrons are paired off. Here 4 ligands there. Each ligand donate a lone pair of electron. So from this description it is clear that 1 4s orbital, 3 4p orbital, resulting the formation of sp3 hybridization. So from this discussion it is clear that as C dot n is 4, it is known as the tetrahedral complex, and as 1s and 3p orbital participate in the hybridization, it is known as sp3 hybridization, undergoes sp3 hybridization. And last one, since all electrons are paired up, the complex is diamagnetic in nature. Let us discuss another example of a square planar complex having C dot n 4. Next we discuss square planar complex. square planar complex having coordination number 4. Let us discuss by giving one suitable example of a complex, that is C dot N 4 having square planar complex. The example is NiCN4 2 minus ion. From this it is clear that the central metal atom is nickel atom having atomic number 28. The noble gas configuration, that is argon 18, 4s2, 3d8. The box-like diagram, that is 3d, then 4s, then 4p. Here 4s2, 3d8, 6, 7, 8. And from this electronic configuration, from this it is clear that we have to calculate the oxidation number. This is the central metal atom, that is X. X plus 4 into minus 1 is equal to minus 2. On solving, X is equal to plus 2. That means nickel present in Ni2 plus ion plus 2 oxidation state. The electronic configuration, argon 18, 3d8. The expected box-like diagram, 3d, 4s, 4p, 1, 2, 3, 4, 5, 6, 7, 8. Mark that. So from this complex, from this formula it is clear that cyanide ion is the strong free ligand. So we know that if there is approach of a strong free ligand, that means the unpaired electron present in the inner d orbital, that is n-1 d orbital, get paired off against the Hund's rule. So mark that. Point 3, that is NiCN4 2 minus, case the box-like diagram, all electrons are paired off. It is 3d, 4s, 4p, 4 ligands are there. Each ligands donate one pair of electron. So from this discussion it is clear that 1 3d orbital, 1 4s orbital and 2 4p orbital get intermixed and resulting the formation of dsp2 hybridization. That is, the expected hybridization is dsp2 hybridization. It is a square planar complex having coordination number 4. And during this box-like diagram it is clear that since all electrons are paired off, the complex is diamagnetic in nature. It is all about the valence bond theory. Next, switch over to the last theory, that is crystal field theory. The last theory of this chapter is crystal field theory. The main postulates of this theory are discussed one by one. The main postulates of this theory are: point 1, in a complex, the central metal atom behaves as a positively charged ion or cation. I repeat again, point 1. In a complex, central metal atom behave as positively charged ion or cation, and the ligands donate their lone pair of electron to the central metal atom or ion. Point 2. All the ligands present in a complex are behave as negatively charged, and also if it is a neutral molecule behave as a dipole. Point 3. The ligands donate lone pair of electron. That means the most important point is that the bond between the cation, that is central metal ion, and the ligand is 100% ionic. I repeat again, the point 3, the most important point. The bond between the cation, means central metal ion, and the ligands is 100% ionic. That is, metal atom and ligand are attached through electrostatic forces of attraction. Next point. Also, the ligand when donate the lone pair of electron to the central metal atom, then there is the development of repulsion of the ligand electron and the electron present in the valence shell of the central metal atom. Next point. As a result of which, the valence electron present in the d orbital of the central metal atom adjusted in such a way that the repulsion is minimum. They placed in such a way that to avoid the presence of a ligand. Next point. As a result, there is the degeneracy of the d orbital is disturbed. Next point. The extent of splitting. The extent of splitting, that is the presence of unpaired electron, which describe the paramagnetic character, depends upon the extent of splitting. That means, greater is the splitting of the d orbital. I repeat again, greater is the splitting of the d orbital, lesser is the chances of presence of unpaired electron. And it is carried out, and this is happening in case of a strong field ligand. I repeat again, greater the splitting of the d orbital, lesser is the chance of presence of unpaired electron, and it is carried out in presence of a strong field ligand. So if there is the presence of a strong field ligand, then it will form inner orbital complex or low spin complex. So let us discuss this concept by taking octahedral complex and tetrahedral complex one by one. First one is octahedral complex. Mark that. In this type of complex, the central metal ion, that is cation, positively charged ion, placed at the center of an octahedron, while the 6 ligands present at the 6th corner of an octahedron. In this case, the 2d orbital, that is ds square minus y square and dz square, these 2d orbital lie at the corner of an octahedron, as a result of which there is the development of greater repulsion. As a result of which there is the increase of their energy from their normal energy level. While another one, that means another, that is dxy, dyz and dzx orbital possess lower energy in comparison to the dx square minus y square and dz square orbital. The difference in energy between the two set of orbital is known as crystal field stabilization energy or crystal field splitting energy in case of octahedral complex, denoted by del O, and in case of tetrahedral complex, it is denoted by del T. Let us discuss it in the form of a diagram. It is known as dxy, dyz, dzx. This set of orbital is known as T to G. It is ds square minus y square, dz square. This set of orbital is known as Eg. The difference, it is known as barycenter. The difference in the splitting of the energy is known as crystal field stabilization energy, that is del O. This one is known as plus 0.6 del O. This one is known as minus 0.4 del O. It is dxy, dyz, dzx, ds square minus y square, dz square. This is the crystal field splitting in octahedral complex. Mark that. This is known as a barycenter. The difference in energy between the two set of orbital is known as crystal field splitting energy or crystal field stabilization energy. In case of octahedral, it is represented by del O. So while going through the electronic configuration for D2 ion, no problem is there. That means all electrons are paired up, that is obeying the Hund's rule. In also D3, but when there is the necessity of a D4 ion, 4 electrons are there. So whether they arranged in pairing form or unpaired form, it is depend upon two factors. One is known as crystal field splitting energy and one is known as pairing energy. Two relations are there. Mark that. Point 1. If del O less than P, that means the crystal field stabilization energy lower than the pairing energy. If this is the case, then the fourth electron will occupy one of the Eg orbital, resulting in the configuration, that is for D4 T to G3 Eg1. Mark that, it is the case, and it is happening only when it is one electron, it is one. That means pairing does not take place, maximum unpaired electron is there, and it is happening in the presence of a weak field ligand. We know the ligands are arranged on the basing upon their del O value. On the basing upon their del O, crystal field stabilization energy value, if the ligands are arranged in increasing order of del O, they form a series known as spectrochemical series. Mark the series. The series is I minus, Br minus, Cl minus, F minus, OH minus, H2O, NH3, next ethylene diamine, carbonyl, cyanide. This is the arrangement of the increasing order of del O. So mark that. Those ligands are present at the low line, that means at the left side of this series, are known as weak field ligand, while those are present at the right line, that means on the right hand side, are known as strong field ligand. That means in this case, so when del O less than pairing energy for D4 configuration, it is DT2G3EG1. It is clear that all electrons remain in unpaired form, and it is possible in case of presence of weak field ligand. So, in case of weak field ligand, there is the probability of, this is the case of D del O less than P. In that case, it is formed inner orbital complex. So in that case, if there is the presence of weak field ligand, then it is formed the outer orbital complex, spin free complex, and maximum chances is the paramagnetic character. Case 2, mark that. Case 2, if crystal field stabilization energy greater than the pairing energy, mark that. The case 2, if del O greater than the pairing energy, then for the D4 configuration, the expected electronic configuration, that is T2G4EG0. Mark that. That means it is remaining this one. It indicates that there is a pairing takes place. That means it is happening in case of a strong field ligand. So it is clear that in case of when del O greater than pairing energy, then there is the presence of strong field ligand. Then it is resulting in the formation of inner orbital complex, low spin complex, and maximum chances is that it is formed diamine complex. And the most important thing that in case of octahedral complex, the lowering energy, that is T2G, is the lowering energy, and EG is the higher in energy. But in case of tetrahedral complex, there is some deviation is there, that is the set of is totally different. Mark that. In case of tetrahedral complex, the arrangement is with the barycenter. It is T2G, it is EG, ds square minus y square, dz square, dxy, dyz, dzx. Here it is known as plus 0.4 del T. It is known as minus 0.6 del T. And the splitting, the difference in energy between the two set of orbital is known as del T. T stands for octahedral complex. This is the difference in the arrangement of in octahedral complex and tetrahedral complex. The most important thing from this discussion, it is clear that the crystal field splitting energy, tetrahedral complex and octahedral complex related as del T is equal to 4 by 9 del O. Mark that, very very important relation is there. That is del T is equal to 4 by 9 del O. I repeat again, the splitting depends upon the nature of the ligand, whether it is weak field ligand or strong field ligand. And it is decided from the spectrochemical series. That is the type of series in which the ligands are arranged in increasing order of their CFAC value. From that series, the ligands present on the low line, that is the left side, are known as weak field. The ligands present on the right side are known as strong field. Then last, we discuss about the magnetic character of a complex. If there is a presence of unpaired electron, then it is paramagnetic nature, and is decided by the parameter known as the magnetic moment, mu. And if all electrons are paired up, there is absence of unpaired electron known as a diamagnetic nature. Then we discuss about color in a complex. Some complex are colored in nature and is due to the DD transition. Mark that. When white light, that is sunlight, fall upon a substance, by gaining the energy, the electron present in the valence shell, that is in B subshell, get excited and jump from lower energy level to higher energy level. And mark that in case of octahedral complex, the electron jump from T to G to Eg, and in case of tetrahedral complex, the electron jump from Eg to T to G in the same subshell. Due to this excitation, due to this jumping of electron, it loses energy in the form of light radiation. That's why a substance looks colored. When it accepts the color from the sunlight, one type of observe one color, and it is we observe its complementary color. And it is possible if there is a presence of unpaired electron. But in some complex, there is an absence of unpaired electron. In that case, there is no DD transition takes place, so that complex are colorless. It is all about the chapter coordination compound.